Look down at the ground beneath your feet. It might look ordinary, like any other patch of earth. But what if I told you that you could be standing directly above a border that's more than 200 million years old? A border you can't see, can't touch, but one that has silently shaped the world as we know it. That's the incredible reality of Earth's hidden geological borders, invisible lines carved by the breakup of the supercontinent Pangaea, lines that still influence where earthquakes strike, where oil pools underground, even where nations draw their boundaries on a map. This isn't just ancient history, it's a living, breathing part of our planet's story, and it's etched right under our feet. Think about that for a moment. Long before humans walked the Earth, continents were on the move. Imagine all of today's landmasses fused together into one colossal supercontinent, surrounded by a single global ocean. That was Pangaea, and then, slowly, powerfully, it began to break apart, not in some catastrophic explosion, but in a magnificent, slow-motion dance driven by forces deep within the planet. Rifts opened, oceans flooded in, and continents began their long journeys to where they are today. But they didn't leave empty-handed. They carried with them the scars and sutures of their shared past. Those scars are the hidden borders we're going to explore. In this video, we're going to retrace that epic journey. We'll dig into the evidence locked in ancient rocks, follow the trails of long-extinct life forms, and use cutting-edge science to map these ghostly divisions. You'll discover how a mountain range in North America shares its roots with one in Europe, how an earthquake in the middle of a continent today might be echoing a crack that formed millions of years ago, and why something as seemingly permanent as a coastline is really just a snapshot in an ever-changing planetary story. So get ready to see the world differently, to look past the surface and right into the deep, dynamic heart of our planet. To understand how this supercontinent broke apart, we first need to journey back to its very creation, to a time long before the dinosaurs, when the map of the world looked utterly alien. Around 335 million years ago, the Earth's scattered continents began a slow, monumental collision course. This wasn't a sudden crash, but a relentless, grinding convergence over tens of millions of years, as tectonic plates carried these giant landmasses together. Imagine watching a slow-motion film of two massive icebergs merging into one. That was the birth of Pangea. This new supercontinent became a colossal, sea-shaped landmass, and it was surrounded by a single, vast global ocean known as Pangaea, meaning all-sea. For the first time in hundreds of millions of years, you could theoretically walk from what is now South Africa to Canada without getting your feet wet. The forces that built this giant were immense and violent. The key mechanism was subduction, where one tectonic plate is forced beneath another into the searing heat of the Earth's mantle. As these plates dove down, they pulled the continents behind them, closing the ancient oceans that once separated them. When these continents finally met, they didn't just bump gently into each other, they crumpled. The incredible pressure of these collisions squeezed the Earth's crust with unimaginable force, pushing up immense mountain ranges that would have rivaled the Himalayas of today. The Appalachians in eastern North America and the Atlas Mountains in northwestern Africa were once part of the same continuous chain, forged in the fiery union of continents. Similarly, the Ural Mountains in Russia stand as a permanent suture, the scar line where the landmasses that became Europe and Asia welded themselves together. This unification did more than just reshape the planet's geography. It fundamentally altered its climate and life. With such a huge landmass, the interior of Pangea became a place of extremes, vast, arid deserts where temperature swings were drastic, far from the moderating influence of the ocean. Unique ecosystems evolved in this connected world, with plants and animals able to spread across this continuous continent. But in creating this single, solid puzzle, the forces of plate tectonics were also, paradoxically, setting the stage for its own destruction. All those massive mountain ranges, those welded together seams between continents, created zones of weakness deep within the crust. The very forces that built Pangaea stored up incredible strain, and the supercontinent's own immense size began to act like a thick blanket, trapping heat from the planet's interior beneath it. This trapped heat would eventually become the engine of its breakup, beginning to dome the land upwards and create the cracks that would tear the world apart. The stage was set for the next great act in Earth's history. But that immense supercontinent, Pangaea, was never destined to last. The very forces that had painstakingly assembled it over millions of years were already beginning to work on tearing it asunder. Deep beneath that solid, unbroken crust, the Earth's engine was rumbling to life. The primary driver of this incredible fragmentation was a process happening far below, in the semi-solid layer of the mantle. Here, massive convection currents were constantly churning, like a pot of thick soup slowly boiling on a stove. These currents are fueled by the immense radioactive heat at the Earth's core, and as that heat rises, it creates colossal plumes of superheated rock that press upwards against the underside of the lithosphere, the rigid outer shell of our planet. This upward pressure from below began to create a colossal dome right in the heart of Pangaea. The supercontinent acted like a giant lid, trapping this incredible heat. As the mantle bulged upwards, it stretched the crust above it, making it thinner, weaker, and hotter. This created a massive zone of weakness, a future fault line on a continental scale. It was here, in this strained and thinning crust, that the first great cracks began to form. These weren't small fissures. They were the beginnings of monumental rift valleys, giant gashes in the Earth's surface that would eventually become the cradle for new oceans. One of the most significant of these was the Central Atlantic Magmatic Province, a truly titanic event. This wasn't just a few volcanoes. It was an apocalyptic-scale volcanic episode, one of the largest in Earth's history, where unimaginable quantities of molten rock flooded to the surface, covering vast areas and filling the atmosphere with gases. This immense volcanic activity further weakened the crust, essentially helping to burn a hole through the supercontinent. This entire process is the fundamental mechanism of plate tectonics in action. The Earth's lithosphere isn't a single, unbroken shell. It's broken into a dozen or so major plates that float on the more fluid asthenosphere below. These plates are constantly, imperceptibly moving, driven by the conveyor belt of those mantle convection currents. In some places, they collide to build mountains. In others, they slide past one another, and in places like the heart of Pangaea, they begin to pull apart. This pulling apart, known as rifting, is a slow but inexorable process. You can think of it like pulling apart a piece of warm taffy. It first stretches, then thins, and finally it tears. This grand geological ballet didn't happen quickly. It unfolded over millions upon millions of years, a timescale almost impossible for us to fully comprehend. The initial rifting began around 200 million years ago, a slow, persistent pulling that would eventually grant the Atlantic Ocean its birth. It was a patient, relentless process, reshaping the entire surface of the planet 1 centimeter at a time. The stage, so carefully set by Pangaea's formation, was now primed for the continents to begin their long, solitary journeys across the globe. And so, with the stage set and the forces of fragmentation in motion, the Earth was ready for its next great act of creation. That immense single crack that began to form in the supercontinent's crust would become the most defining geological feature of our modern world. the Atlantic Ocean. Picture this: around 200 million years ago, the colossal landmass of Pangaea began to experience a profound continental headache. The tremendous heat building up beneath it from the mantle plume needed an escape route. The crust, stretched thin and weakened over millions of years, could no longer hold. It began to fracture, not with a dramatic bang, but with a prolonged, earth-shattering groan. This wasn't a single event, but a process, a colossal zipper slowly unzipping from north to south, beginning to separate what we now know as North America from Northwest Africa. The initial evidence of this divorce is still visible today, etched into the landscapes of both continents. If you look at a map, you can still see the incredible puzzle piece fit between the coastlines of eastern South America and western Africa. But on the ground, the story is even more compelling. In places like the Palisades Sill in New Jersey or the massive basalt flows of the Newark Basin, we find the scars of this continental breakup, ancient lava that flooded into the growing Rift Valley. This valley would have been a dramatic landscape, a colossal gash in the earth thousands of miles long, flanked by high cliffs, with volcanoes spewing ash and rivers flowing down into a vast, low basin. It was a world tearing itself in two. As the two continental plates continued to pull apart, something miraculous happened in the gap between them. The pressure release caused by the separation allowed material from the underlying mantle to rise up. This wasn't a violent volcanic explosion, but a persistent, steady welling up of magma from below. This molten rock would spill out, cool in the water, and solidify, creating brand new oceanic crust. This process, happening continuously along the entire length of the rift, formed the foundation of the Mid-Atlantic Ridge. Think of this ridge not as a simple mountain range, but as a dual conveyor belt running in opposite directions. As new magma rises at the ridge, it pushes the older, previously formed crust outward, away from the center. This is the engine of seafloor spreading, and it's why the Atlantic is still growing wider today, at about the same speed your fingernails grow. This slow but relentless zipper effect didn't just create a new ocean basin, it began to permanently rewrite the planet's rulebook. As the Atlantic Ocean grew, it fundamentally altered global climate patterns. The single, massive global ocean, Panthalassa, was now being divided. New currents began to form, circulating warm water from the equator toward the poles and cool water back again, creating the climate systems we recognize today. This reorganization of the oceans also had a profound impact on the evolution of life. Marine species that were once part of a single, connected population were suddenly separated by an ever-widening moat of deep water. This geographical isolation became a powerful driver of evolution, forcing species on either side of the new ocean to adapt to their new environments independently, leading to an explosion of new life forms. The birth of the Atlantic Ocean did more than just add a blue feature to the map. It established one of the most significant and enduring geological borders on Earth. This watery divide, which seems so permanent to us, hides a violent, fiery origin story beneath its waves. The Mid-Atlantic Ridge is a submerged monument to this ongoing process, a reminder that the planet is still dynamic and alive. But this was far from the end of the story. The breakup of Pangea was a chain reaction. The creation of the Atlantic was just the first, and perhaps the most iconic, domino to fall in a global reorganization that would eventually rip the entire supercontinent into the fragmented world we know today. But as the continents drifted apart, they left behind more than just the widening gulf of the Atlantic Ocean. They also left behind their own hidden scars, ancient wounds from their initial collision that were stitched shut deep within the Earth's crust. These are known as geological sutures, and they are some of the planet's most profound and invisible borders. Imagine two continents crashing together with unimaginable force. The ocean floor that once separated them doesn't just vanish. It's forced downward, subducted into the mantle, where it's largely consumed by the intense heat. The point where the two continental plates finally weld together, often marked by a line of mashed-up rock and slivers of that ancient ocean floor, is the suture zone. It's the geological equivalent of a massive surgical scar, buried under eons of new rock, soil, and life. A perfect example of this is the Iapetus suture, which runs roughly along the border between England and Scotland. Hundreds of millions of years ago, a vast ocean called the Iapetus separated the ancient continents of Avalonia and Laurasia. Their eventual collision consumed that ocean and fused the landmasses together, creating the foundation of the British Isles. Today, that boundary is completely invisible on the surface, hidden beneath rolling hills and cities, but it's there, a deep-seated line of weakness in the bedrock. And this isn't a unique case. All around the world, from the Alps to the Himalayas, similar sutures mark where Earth's continents have been stitched together and torn apart again over billions of years. So how do we find these hidden borders we can't see? Modern geologists have an incredible toolbox at their disposal. One key method involves studying the magnetic signature of rocks. When volcanic rock forms, tiny magnetic minerals within it align themselves with the Earth's magnetic field at that time, essentially freezing a compass direction into the stone. By carefully mapping these magnetic anomalies across a landscape, scientists can detect where rocks with completely different magnetic histories are suddenly sitting right next to each other, a clear sign of a colossal tectonic boundary. Another crucial technique is radiometric dating, which measures the precise age of rocks. Finding a sharp, straight line where billion-year-old rock abruptly meets much younger rock is a giant red flag pointing to a suture zone. Perhaps the most powerful tool is seismic imaging, which works like a giant ultrasound for the planet. By measuring how sound waves generated by small earthquakes or deliberate explosions travel through and bounce off different layers of rock deep underground, geologists can create detailed three-dimensional maps of the subsurface. These maps can reveal the distinct, angled patterns of rock layers that were crumpled and thrust together during a continental collision, clearly outlining the ghost of an ancient suture. Why does this matter today? Because these cryptic lines are far more than just historical curiosities. They represent zones of profound weakness in the Earth's crust. The rock along these old scars is often heavily fractured and unstable, making it easier for stress to build up and release. This means that many of the earthquakes that shake continents far from the edges of tectonic plates often occur along these ancient sutures. They are also hotspots for mineral deposits. The same forces that mashed continents together often funneled metal-rich fluids into these fracture zones, creating concentrated veins of valuable resources like gold, copper, and zinc. Understanding where these sutures lie is therefore crucial for both assessing natural hazard risks and guiding resource exploration. They are active, influential players in our modern world, a permanent reminder that the ground beneath our feet carries the deep and dynamic memory of its past. Now, if you were to stand atop the Appalachian Mountains in the eastern United States and somehow gaze across the Atlantic Ocean, you might notice something astonishingly familiar about the landscape in Scotland and Norway. The rolling, ancient hills there share an uncanny resemblance because, geologically speaking, they are the very same hills. These sprawling mountain belts, now separated by thousands of miles of ocean, were once a single, continuous range that stretched across the supercontinent of Pangaea, a colossal spine formed in the fiery collisions that built the world. When Pangaea eventually broke apart, this mighty range didn't vanish. It was simply bisected, its two halves carried away on separate continental rafts, creating one of the most compelling and visible geological borders in Earth's history. The evidence for this incredible connection is locked in the rock itself. Geologists can match not just the types of rock, but their precise ages and the order in which they were laid down, like matching the torn pages of a book found in two different countries. The Appalachian Mountains and the Caledonian Mountains in Europe are both composed of incredibly old, deformed rocks, metamorphic rocks like schist and gneiss that were baked and twisted under immense pressure, alongside ancient volcanic rocks and marine sediments. The sequence of these layers, the specific minerals within them, and the unique signatures of their formation are virtually identical on both sides of the Atlantic. It's a perfect geological fingerprint match, proving these now distant landmasses were once seamlessly joined, but the proof doesn't stop with the rocks. The very structure of these mountains tells the same story of a shared, violent birth. Detailed geological mapping reveals that the folds and faults, the colossal wrinkles and tears in the Earth's crust, line up perfectly when you mentally push the continents back together. The direction of the thrust faults, the angles of the folds, all of these structural details point to a single, unified mountain-building event known as the Caledonian orogeny. This was a period of monumental tectonic crunching that occurred over 400 million years ago, when the ancient continents of Laurasia and Baltica collided, squeezing the ocean between them and pushing up this mighty mountain chain. The breakup of Pangea later pulled this single range apart, leaving its roots on opposite shores. Perhaps the most delightful clue comes from the fossils embedded within these rocks. In the sedimentary layers that were deposited along the flanks of these ancient mountains, paleontologists find identical fossils of small, archaic marine creatures that lived in the shallow seas surrounding the range. These species had very limited ranges and could not have crossed a vast ocean. Finding the exact same fossilized trilobites or brachiopods in the rocks of Newfoundland and the rocks of Western Scotland is like finding a piece of the same unique pottery at two different archaeological sites. It's undeniable proof that these sites were once part of the same neighborhood. The continents themselves carry this biological memory, a silent testament to their former unity. These bisected mountain ranges are far more than just a fascinating geological curiosity. They are active players in our modern world. The deeply buried roots of these ancient mountains, known as basement rock, continue to influence everything that happens above them. They create zones of weakness that can guide the course of modern rivers, determine the location of new mountain ranges, and even influence where earthquakes might occur. They act as a foundational template, a deep-seated geological border that continues to subtly shape the landscape millions of years after their formation. They stand as silent, stoic sentinels, bearing witness to the incredible forces that first built a supercontinent and then tore it asunder, reminding us that the Earth's crust has a long and indelible memory. While the mighty mountain ranges tell the story of the continents above the waves, the deepest, darkest parts of the ocean floor hold an even more precise record of Pangea's breakup. Scattered across the abyssal plains are long, linear scars known as fracture zones, some of the most enigmatic and revealing geological borders on the planet. To understand them, we have to go back to the engine of continental drift, the mid-ocean ridge. This isn't a single, continuous mountain chain. Imagine it instead as a series of segments, slightly offset from one another like the pieces of a broken pane of glass that have been shuffled apart. These offsets are where the incredible forces of plate tectonics play out in a side-to-side motion. As new oceanic crust is born at the ridge and pushed outward, the plates on either side of these offsets don't just move apart, they also have to slide past each other horizontally. These sliding boundaries are called transform faults, and they are the active, seismically alive parts of the system. But the story doesn't end there. As this newly formed crust continues to travel away from the ridge, it cools, contracts, and sinks deeper into the mantle. The transform fault, which was only active at the ridge, leaves behind a permanent scar on the aging ocean floor, a fracture zone. This is an inactive line of weakness, a fossilized trace of that original transform motion, stretching for thousands of kilometers across the seafloor. A prime example of this is the Charlie Gibbs fracture zone in the North Atlantic, one of the largest and most significant of these features. It's a massive, dual-peaked underwater scar that stretches for over 2,000 kilometers, virtually cutting the mid-Atlantic ridge in half. Its orientation is not random. It's a direct compass pointing back to the original direction of the continental separation. When North America and Africa first began to rift apart, the direction of pull was not perfectly straight. The continents tore along a specific path of least resistance, and the fracture zones, like the Charlie Gibbs, were frozen into the newborn oceanic crust, recording that initial direction of travel like a set of ancient tire tracks. Though hidden beneath kilometers of water, these features have a profound impact on the world we see. They create massive underwater ridges and valleys that act like mountain ranges and canyons in the deep sea, dramatically steering the flow of deep ocean currents. These currents are the great conveyor belts of the Earth's climate, transporting heat, nutrients, and dissolved gases around the globe. By channeling this flow, fracture zones help dictate where nutrients well up from the depths to feed vast plankton blooms, which in turn support incredible concentrations of marine life, from great whales to entire commercial fishing industries. They are invisible architects of the deep sea ecosystem. For geologists and resource explorers, these zones are like a historical archive. By meticulously mapping the pattern and orientation of fracture zones across an ocean basin, scientists can rewind the tape of plate motions with astonishing accuracy. They reveal not just the direction, but sometimes even the speed and the pauses in the continental drift. Furthermore, the fractured rock of these zones often acts as a trap for valuable minerals and metal-rich deposits that precipitate out of hot fluids circulating from the Earth's interior. They are, in a very real sense, treasure maps leading to the riches generated by our planet's restless geological activity, preserving the fingerprints of Pangea's dissolution in the perpetual darkness of the abyssal plain. This process of continental stretching and thinning is precisely what forged the submerged borders we now call continental shelves and margins. Picture a vast, flat, underwater plain gently sloping away from the beach, sometimes for hundreds of miles, before it finally plunges into the deep, dark abyss of the open ocean. That is the continental shelf, and its outer edge, the continental slope, marks one of the most significant hidden geological borders on the planet, the true boundary between the relatively lightweight granite of the continents and the dense, heavy basalt of the ocean floor. These aren't just passive underwater landscapes, they are the direct and dramatic result of the continents being pulled apart. As North America and Africa began their slow separation, the crust between them didn't just crack cleanly. It stretched like warm taffy, becoming thinner and thinner. This stretched crust sank lower, and over millions of years, it was eventually flooded by rising sea levels, creating the wide, shallow platforms we see today. To understand the sheer scale of this transformation, consider the eastern North American margin. Today, it's the bustling coastline from Florida to Maine, but 200 million years ago, this was the very heart of the Rift Valley, a dusty, volcanic inland basin far from any ocean. The rocks under modern-day cities like New York and Baltimore are the same faulted and fractured rocks that were once contorted by the initial tearing of Pangea. As the Atlantic Ocean basin widened, this stretched crust cooled, subsided, and sank, becoming a passive margin, a stable, trailing edge of a continent that is slowly being buried by sediments eroding from the land. This immense pile of sediment, thousands of feet thick, is what creates the incredibly fertile grounds for both biology and resources. The economic and ecological significance of these drowned borders cannot be overstated. These sunken plains are among the most biologically productive places on Earth. Sunlight penetrates the shallow waters, fueling massive blooms of phytoplankton, which form the base of a complex food web. This is why the world's most productive fisheries, think of the Grand Banks off Newfoundland or the North Sea, are all located over continental shelves. These areas are literal breadbaskets for humanity, but the riches go far deeper. Those same layers of sediment that accumulated over eons are also perfect traps for organic material. Heat and pressure have cooked this material into vast reservoirs of oil and natural gas. The entire North Sea oil industry, for instance, is based on extracting hydrocarbons from the sediments of a failed rift arm, a geological feature that began to form during the breakup but never quite made it to a full ocean. The North Sea provides a fascinating counterexample. It represents a rift system that started to pull apart but ultimately failed. Instead of progressing into a new ocean, the stretching stopped, leaving a broad, depressed basin that was later flooded. This failed rift, still a zone of weakness, continues to influence Europe, from its resource distribution to its potential for subtle seismic activity. These continental margins, therefore, are not merely inert relics. They are dynamic archives and active economic zones. They tell a dual story of creation and loss, the creation of new oceanic frontiers and the loss of ancient terrestrial landscapes beneath the waves. They are a testament to the fact that some of the most important boundaries on Earth are the ones we cannot see, hidden beneath the sea, yet they dictate where we find food, fuel, and a profound connection to our planet's deep past. While the fracture zones on the ocean floor record the direction of plate movement, there's another, even more dramatic feature that acts like a permanent fingerprint of a continent's journey, a volcanic trail. These aren't random chains of undersea mountains. They are a precise record of a continent drifting over a fixed, superheated fountain of magma from deep within the Earth's mantle, known as a hotspot. To understand how this works, picture a piece of paper slowly moving over a stationary candle flame. The flame will burn a series of holes in the paper. The oldest hole will be farthest from the flame, and the newest hole will be directly above it. Now, imagine that the paper is a tectonic plate and the candle flame is a mantle hotspot. The series of burned holes is a chain of volcanoes and seamounts, telling you exactly which way the plate was moving and how fast. This isn't just a theoretical idea, we see it happening right now. The most famous example is the Hawaiian Islands. The big island of Hawaii is currently sitting over the hotspot with its active volcanoes like Kilauea. But as you look northwest along the Hawaiian chain, the islands get progressively older, more weathered, and eventually become submerged seamounts all the way to the Aleutian Trench. This is the volcanic trail, a clear path showing that the Pacific Plate has been moving northwest for millions of years. But hotspots weren't just passive observers of Pangea's breakup. Many geologists believe they were active instigators. Colossal mantle plumes, like the one that now sits beneath Iceland, or the one that formed the Tristan da Cunha hotspot in the South Atlantic, are thought to have risen up and pressed against the underside of Pangaea like a blowtorch. This immense thermal energy would have significantly weakened the supercontinent's thick lithosphere, doming it upwards and helping to initiate the rifting process that eventually tore it apart. The evidence for this is written across the ocean floor in spectacular fashion. Lying off the coast of New England is a breathtaking underwater mountain range known as the New England Seamounts. This is the oldest part of a much longer trail that includes the corner rise seamounts and continues all the way to the active volcanoes of the Great Meteor Hotspot near the Mid-Atlantic Ridge. This chain is not a random scattering, it's a perfectly linear progression. The oldest seamount, Nashville, is located farthest to the west and is around 80 million years old. As you travel southeast along the chain, each subsequent seamount is younger, with the youngest being located closest to the hotspot's current position. This trail was created because the North American plate has been steadily moving west-southwest for the last 100 million years, drifting away from the Mid-Atlantic Ridge and over the stationary hotspot. It is a perfect natural GPS track log frozen in stone on the seafloor. This provides geologists with something incredibly valuable, an independent clock to calibrate the story of continental drift. By dating the rocks from each volcano in a seamount chain, scientists can calculate the speed of the plate's movement with remarkable precision. If two volcanoes are 300 miles apart and one is 30 million years older than the other, we know the plate moved at an average speed of 1 centimeter per year over that period. This data perfectly corroborates the spreading rates calculated from the magnetic stripes on the seafloor, giving us a multi-pronged and incredibly robust understanding of plate motions. These fiery landmarks, from the submerged peaks of the New England seamounts to the active fury of Iceland, are more than just geological curiosities. They are nature's immutable navigational beacons, tracing the long and wandering paths that continents have taken since the Great Divorce of Pangea, offering us undeniable clues to the powerful forces that both build our world and tear it apart. So far, we've traced Pangea's story through the language of rocks, mountains, and ocean floors, but some of the most compelling evidence for this supercontinent isn't written in stone, it's preserved in bone and leaf. Long before geologists had seismic imaging or paleomagnetism, they had fossils, and these ancient remains told a story that was, at first, utterly baffling. How could anyone explain the discovery of identical, freshwater reptiles in the rocks of Brazil and southwest Africa, or the exact same fossilized fern found in the frozen, barren soils of Antarctica, the coal mines of India, and the plains of Australia? For scientists in the 19th century, these were profound mysteries. The most logical explanation, which seemed wildly speculative at the time, was that these now separated continents were once intimately connected, allowing land-based creatures and plants to roam freely across a unified world. This field of study is known as paleobiogeography, a complex word for a beautifully simple concept, using the geographic distribution of ancient life to map the Earth's forgotten geography. It treats fossils not merely as curiosities, but as biological road signs pointing to lost highways and bridges between continents. A perfect example is the Glossopteris plant. This was no delicate flower, it was a robust woody seed fern that grew in dense, swampy forests. Its fossils, with their distinctive tongue-shaped leaves and seeds too heavy to be carried by wind across an ocean, have been found in tremendous abundance across all the southern continents. Finding a Glossopteris fossil in Antarctica is like finding a piece of a palm tree there today. It simply doesn't make sense given the current climate and position of the continent. The only explanation is that Antarctica was once in a much warmer, wetter latitude, nestled right against the other southern landmasses as part of a larger continental body we now call Gondwana. This plant is such a powerful marker that its presence alone is enough for a geologist to confidently identify a rock sequence as being from that specific time period when the supercontinent was still whole. The animal kingdom provides an equally powerful case with a group of reptiles known as mesosaurs. These were small, freshwater predators that lived in lakes and rivers. Their fossils are found exclusively in two places, the Paraná Basin of Brazil and the Karoo Basin of South Africa. A mesosaur could no more have swum the thousands of kilometers of frigid, salty Atlantic Ocean than a lizard could today. Their presence on both sides of the ocean is irrefutable proof that these two regions were once part of the same river system on the same continent. When South America and Africa split apart, they literally tore that ancient river valley in two, stranding populations of mesosaurs on either side. For these creatures, the Atlantic Ocean became a biological border that hadn't existed before, a barrier that would eventually seal their fate as the environments on each side began to change independently. And that's where the story takes its next fascinating turn. The very same geological forces that created these new oceanic borders became the great engine of biological diversity. Once a population of animals or plants is physically separated by a barrier like a new ocean or a widening rift valley, their evolutionary paths diverge. This process is known as vicariance. The individuals on one continent, facing a unique set of predators, climates, and food sources, begin to adapt in different ways than their cousins on the other continent. Over millions of years, these small changes accumulate, leading to the development of entirely new species. This is why we see such dramatic and unique life forms on continents that have been isolated for long periods. Australia is the classic example. After it broke away from Antarctica and drifted into isolation, its cargo of marsupial mammals evolved without competition from placental mammals, leading to the incredible array of kangaroos, koalas, and wombats we know today. Similarly, the lemurs of Madagascar evolved their unique forms after that island fragment was separated from the African mainland. These fossil time capsules do more than just prove a theory. They allow us to reconstruct the ancient world with astonishing detail. By mapping where specific fossils are found, scientists can almost draw the shorelines of those long-vanished continents and trace the outlines of their ancient river deltas and inland seas. They tell a story of a lost world of connected forests and shared fauna, a world that was shattered by tectonic forces. That breakup, while ultimately leading to extinction for species like the mesosaurs, also provided the creative spark for the incredible tapestry of life we see across the globe today. The biological borders that now define our world's ecosystems were forged in the fiery fragmentation of a supercontinent, a permanent reminder that the history of life and the history of the Earth are one and the same. The fragmentation of Pangea did far more than just redraw the world map. It completely rewired the planet's climate system, setting in motion a chain of events that would dictate where deserts formed, where forests flourished, and even where human civilizations could eventually take root. When all the continents were fused together into one massive supercontinent, the climate was dominated by a phenomenon known as continentality. The vast interior of Pangea, far from the moderating influence of the ocean, became a land of extreme scorching hot days, freezing cold nights, and desperately arid conditions. Global circulation was relatively simple, with moisture-laden winds struggling to penetrate the heart of the giant landmass. But as the continents began their slow drift, they opened up new seaways and closed others, creating and dismantling ocean currents that act as the planet's central heating and cooling system. One of the most profound climate-changing events was the opening of the Drake Passage. For millions of years, South America and Antarctica were connected, part of the southern supercontinent of Gondwana. This land bridge prevented the free flow of water between the Pacific and Atlantic Oceans. But around 40 million years ago, as the tectonic forces continued to pull the continents apart, this connection finally severed. The result was one of the most powerful and important ocean currents on Earth, the Antarctic Circumpolar Current. With no continent to block its path, water could now flow unimpeded around the entire globe in a continuous, frigid loop. This current effectively isolated Antarctica from the warmer waters to the north, transforming it from a forested continent into the frozen, ice-covered landmass we know today. The formation of this permanent ice sheet had a cascading effect, lowering global sea levels and sucking moisture out of the atmosphere, which contributed to a significant drop in worldwide temperatures and helped usher in the ice ages. This single geological event, the opening of a gateway, didn't just change the weather, it changed the entire thermal regime of the planet. Simultaneously, the northward journey of other continents like Africa and India was creating entirely different climate patterns. As India plowed into Asia to create the Himalayas, it dramatically altered atmospheric circulation. The presence of this massive, high-altitude plateau began to intensify seasonal wind patterns, supercharging the monsoon systems that billions of people in Asia and Africa depend on for their agriculture today. These aren't gentle rains, they are deluges driven by the temperature difference between the rapidly heating land and the cooler ocean. The breakup of Pangea positioned continents in such a way that these monsoonal cycles could become powerful and reliable features of the climate. Conversely, the same process created some of the world's great deserts. The Sahara, for instance, exists in its current hyper-arid state partly because of the position of the African continent relative to the global circulation cells that push dry, descending air down onto the tropics. The creation of the Atlantic Ocean also played a role, as the cold Canary Current flowing along its northwest African coast chills the air above it, reducing its ability to hold moisture and further starving the adjacent land of rain. These new environmental borders, the line between a lush monsoon forest and a barren desert, or the frigid barrier of the Southern Ocean, became powerful drivers of evolution. Species that had once roamed across connected landscapes suddenly found themselves isolated by climate. A population of animals adapted to a warm, wet environment might be cut off from its relatives by the spread of an impassable desert, forcing each group to adapt to their new, distinct realities. This geographical and climatic isolation accelerated the evolution of new species, creating the incredible biodiversity we see in today's ecosystems. The distribution of life on Earth is a direct map of these ancient climatic borders. Furthermore, these climate patterns, established tens of millions of years ago, went on to silently guide the course of human history. Civilizations flourished in the fertile belts of reliable monsoon rains like the Indus Valley, while the vast deserts acted as natural barriers, influencing trade routes, migration patterns, and the rise and fall of empires. The story of Pangea's breakup is a stunning reminder that the ground beneath our feet doesn't just hold up our cities. It fundamentally shapes the very air we breathe and the water we drink, connecting the deep time of geology to the daily reality of life on Earth. Just as the breakup of Pangea drew new coastlines and mountain ranges on the map of the world, it also drew something far more consequential for human civilization: the invisible borders of immense wealth. The very same tectonic forces that tore continents apart became the master architects of our planet's mineral and resource distribution, creating economic boundaries that have, for centuries, dictated global power, fueled conflicts, and built nations. When we look at a modern political map, we see borders defined by rivers, mountains, and treaties, but superimposed upon that is a much older, hidden map, a treasure chart written in the language of geology. Its X marks the spot placed hundreds of millions of years ago during the supercontinent's fragmentation. This profound connection is most dramatically illustrated by the oil-rich basins that now line the opposing coastlines of the Atlantic Ocean. The process of continental rifting that created the ocean was not a clean break. It was a prolonged period of stretching, thinning, and violent volcanic activity. As North America and Africa were wrenched apart, the crust between them subsided, creating a series of deep, sediment-filled basins known as passive margins. These basins became the perfect cradle for life and ultimately for oil. Ancient rivers carried immense amounts of organic material, dead plants and microscopic marine organisms into these newly formed depressions. Over millions of years, this organic soup was buried under ever-thickening layers of sand and mud. The heat from the Earth's interior and the immense pressure from above slowly cooked this material, transforming it into the hydrocarbons we now depend on. The incredible part is that this process happened symmetrically. The same geological conditions that created the oil-rich basins off the coast of Brazil were simultaneously creating identical basins off the coast of West Africa. This is why today geologists can look at seismic data from the Santos Basin in Brazil and see a nearly perfect mirror image in the Kwanza Basin of Angola. The oil reserves were literally a shared inheritance before the continents even parted ways. This story of shared geological wealth extends far beyond oil to the solid minerals that power our modern technology. One of the most striking examples is the famous African Copper Belt, a vast mineral-rich zone stretching through Zambia and the Democratic Republic of Congo. This region is one of the world's most prolific sources of not just copper, but also cobalt, a critical element for batteries in electric vehicles and electronics. For decades, its existence seemed like a unique geological fluke. That is, until geologists looked across the Atlantic to South America. There, in eastern Brazil, lies an almost identical copper-cobalt province. The rock types, the age of the deposits, and the specific way the minerals were concentrated are a perfect match. The only logical conclusion is that these two mineral belts were once a single, continuous zone that was catastrophically split in two when South America ripped away from Africa. The riches were literally torn asunder and drifted to opposite sides of the ocean. Understanding this ancient connection is far more than an academic exercise. It is a powerful tool that directly reduces the financial risk and environmental footprint of modern resource exploration. Instead of randomly drilling expensive test wells or digging exploratory mines across a vast continent, geologists can use the known locations of mineral deposits on one continent to make highly educated predictions about where to look on its ancient neighbor. If a specific type of gold deposit is found consistently along a particular geological structure in Ghana, there's a high probability that the same deposit exists along the continuation of that very same structure in northeast Brazil, once you mentally reassemble the continents. This predictive power transforms exploration from a high-stakes gamble into a more precise science. It allows companies to focus their efforts, which means fewer drilled holes, less land disturbance, and a significantly lower environmental impact in the search for the resources our world needs. The Ghost of Pangea, therefore, doesn't just show us where the treasure is buried. It hands us a map that allows us to dig more responsibly. These hidden geological borders, forged in fire and chaos so long ago, continue to silently guide the flow of global commerce and define the economic destinies of nations, proving that the ground beneath our feet is the ultimate archive of both planetary history and human opportunity. This relentless geological restructuring didn't end 200 million years ago, it's still happening right now. And the very same weaknesses created during Pangea's breakup continue to shape where and how the Earth unleashes its raw power through earthquakes and volcanic eruptions. Think of the planet's crust not as a solid, unbroken shell, but as a pane of glass that was once shattered and then imperfectly glued back together. Those old fault lines and sutures are the places most vulnerable to new stress, and today they serve as the hidden borders for some of the world's most significant natural hazards, a direct and ongoing legacy of the supercontinent's dissolution. Perhaps the most dramatic example of this living legacy is the East African Rift System, a place where you can literally see a continent in the process of tearing itself in two. Stretching over 3,000 miles from the Red Sea down to Mozambique, this colossal geological wound is a network of deep valleys, steep cliffs, and towering volcanoes. This rift is not a new feature. It is the reactivation of an ancient fundamental weakness in the crust, a zone where Pangea was once stitched together and is now, millions of years later, coming apart again. Here, the Nubian plate and the Somali plate are slowly diverging at about the same speed your fingernails grow. As they pull apart, the crust in between stretches, thins, and fractures, causing frequent, often felt earthquakes. Magma from the mantle rises up to fill the gaps, fueling spectacular volcanic systems like Mount Kilimanjaro and Mount Nyiragongo, whose destructive potential is a constant concern for the millions of people living in the Rift Valley. This region is a living laboratory, offering a stunning glimpse into the very same rifting processes that first cracked Pangea open and began forming the Atlantic Ocean. But you don't have to be on a continent that's actively splitting to feel the echoes of this ancient breakup. Even along the so-called passive margins of the Atlantic Ocean, far from the active grinding of plate boundaries, the Earth occasionally shudders. The city of Charleston, South Carolina, experienced a devastating earthquake in 1886, a seismic event that seemed to come out of nowhere, located hundreds of miles from the nearest tectonic plate boundary. Geologists now understand that these intraplate earthquakes are likely the result of stresses being transmitted inward from the active mid-Atlantic ridge, reactivating those old, deeply buried faults that were created during the initial rifting phase. The crust here remembers its traumatic birth, and when enough stress builds up along these prehistoric scars, they can slip, shaking the ground with a force that defies our expectations of geological stability. These events are a powerful reminder that the boundaries of seismic risk are not always where our maps say they should be. They are also drawn along the invisible, forgotten scars from the planet's deep past. The practical importance of understanding this deep time connection cannot be overstated. By mapping these ancient zones of weakness, seismologists and geologists can dramatically improve our models for assessing earthquake risk. A city built directly over a buried suture zone or a failed rift arm, even in the middle of a tectonic plate, may be at a much higher risk for damaging earthquakes than previously thought. This knowledge directly influences building codes, emergency preparedness plans, and the siting of critical infrastructure like dams, power plants, and hospitals. It allows us to move from a reactive stance to a more proactive one, potentially saving countless lives and billions of dollars in damage. The study of Pangea's breakup is therefore not just an academic pursuit into Earth's history. It is a crucial tool for safeguarding our future. The ground may seem solid and permanent beneath our feet, but it is a dynamic, ever-changing system, and its ancient impulses continue to shape the world we live in today, reminding us that the planet's story is far from over. It's easy to look at a map of the world and see political borders as purely human inventions, lines drawn by kings and cartographers, the results of wars and treaties. But if you pull back the lens of time, you start to see a far deeper story. The very ground beneath our feet, shaped by the fragmentation of Pangea, has been a silent and powerful partner in writing human history, subtly directing the flow of people, commerce, and conflict for thousands of years. Long before diplomats ever put pen to paper, the Earth itself was drawing the first drafts of our maps through the language of geology, the paths carved by rivers, the barriers erected by mountains, and the hidden treasures buried in the rock. Consider the Appalachian Mountains, a range we discussed earlier as the ancient, bisected sibling of Scotland's highlands. For early European settlers in North America, this massive geological wall presented a formidable obstacle. Its rugged, forested ridges and valleys acted as a natural bottleneck, funneling migration southward and slowing the westward expansion of the 13 original colonies for generations. This physical barrier didn't just influence exploration, it had profound political consequences. It helped define the early cultural and economic boundaries of the fledgling United States, creating a distinct backcountry frontier that often had more in common with its neighboring regions than with the coastal power centers. The mountains, a remnant of Pangea's formation, became a de facto border, shaping settlement patterns that would later influence state lines and even the allegiances of the Civil War. On the other side of the Atlantic, the Rhine River Valley in Europe tells a similar story of geological destiny. This isn't just any river valley, it's a massive rift system, a geological wound that began tearing open tens of millions of years ago, a process that continues to make the region seismically active today. This sinking block of crust created a wide, flat, and incredibly fertile pathway that cuts directly through the heart of Western Europe. For millennia, the Rhine has been more than a river, it has been a highway. The Romans used it as a natural border for their empire, the Limes. In the Middle Ages, its banks were dotted with castles built to control trade and levy tolls on the constant flow of goods. Today, it remains one of the world's busiest waterways, and its course helps define the borders of multiple modern nations. The river valley, a direct result of much older tectonic forces, provided the fertile soil for farming, the easy route for transportation, and a natural line of defense that has been fought over for centuries. It is a perfect example of a geological feature silently scripting the narrative of human cooperation and conflict. This influence extends far beyond obvious physical barriers to the hidden distribution of resources we discussed earlier. The location of valuable mineral deposits or oil reserves determined by those ancient rifting events has directly fueled economic booms, dictated colonial ambitions, and drawn the borders of wealth and poverty across the globe. The coal fields that powered the British Empire, the gold deposits that sparked rushes and built nations, the oil that defines modern geopolitics, all of these are ultimately tied to the planet's deep tectonic history. A border drawn today to encompass an oil field is, in a very real sense, a border that was first drawn by the breakup of a supercontinent 200 million years ago. Communities flourish where the geology provides water and fertile soil. They are abandoned where it does not. Trade routes snake through mountain passes that were carved by ancient glaciers, following paths of least resistance that were established eons before humans walked the earth. Even the sites of great battles are often chosen not just by generals, but by the landscape itself, a strategically placed hill, a defensible river crossing, all features inherited from a distant geological past. So the next time you look at a political map, try to see the ghost of a geological one lurking beneath the surface. Those straight lines in parts of Africa and the Americas, often criticized as arbitrary colonial impositions, sometimes overlap startlingly with much older, invisible boundaries, the edges of sedimentary basins holding oil or minerals, or the limits of a groundwater aquifer that made one area viable for settlement and another not. Geology doesn't dictate every human decision, but it sets the stage upon which our history unfolds, providing the opportunities and the limitations that every culture must navigate. It is the silent, unchanging partner in the dance of human civilization, reminding us that the ground we stand on is not just a platform for our lives, but an active participant in our story, its ancient history forever imprinted on our modern world. But how can we possibly know with such certainty the precise paths these wandering continents took? How do we trace journeys that unfolded over millions of years, long before any human was around to witness them? The answer lies not in ancient maps or journals, but locked within the rocks themselves, in a field of science that acts as a time-traveling compass: paleomagnetism. This incredible technique allows us to read the history of the Earth's magnetic field, which has been faithfully recorded by certain minerals in volcanic rock since the moment they cooled from molten lava. When a magnetic mineral like magnetite, essentially a tiny piece of natural iron, cools past a specific temperature called the Curie point, it becomes magnetized, aligning itself perfectly with the Earth's magnetic field at that exact time and place. It's like a microscopic compass needle freezing in position, capturing a snapshot of where north was and how strong the field was, potentially hundreds of millions of years ago. Geologists can extract this ancient information by carefully drilling cylindrical samples out of rock formations, and then analyzing them in a laboratory instrument called a magnetometer, which is sensitive enough to detect the faint, fossilized magnetic signature. This data reveals two absolutely crucial pieces of information: the direction to the magnetic pole and the magnetic latitude at which that rock formed. It tells us not just where a continent was, but also how it was oriented. A rock showing a magnetic inclination that indicates it was near the equator, for instance, could not possibly have formed at its current location in a high latitude. The only logical conclusion is that the entire continent must have moved. This was the final, irrefutable proof that settled the debate over continental drift. By collecting and analyzing rocks of different ages from the same continent, scientists can essentially create a motion picture of that landmass's journey across the globe, frame by ancient frame. The most compelling visual representation of this data is something called an apparent polar wander path. Now, the name is a bit of a misnomer. It's not that the magnetic poles themselves have wandered wildly over time. Instead, these paths track how the position of the magnetic pole appears to have moved from the perspective of a fixed continent. If a continent had remained perfectly still for the last 300 million years, its polar wander path would be a single point. The North Pole would always have appeared to be in the same place. But that's not what we see. For North America, the path drawn by rocks of increasing age shows a long, slow, and curving track from somewhere near modern-day Japan, across Siberia, and finally to its current position over the Arctic Ocean. This path clearly shows that the continent has rotated and drifted enormous distances. The real magic, the true smoking gun for Pangea, appears when you compare the polar wander paths of different continents. For example, if you plot the 300-million-year-old path for North America and the same aged path for Europe, they don't come close to lining up with today's geography. But if you mentally slide the continents back together, closing the Atlantic Ocean as if it were a book, those two separate paths suddenly merge into one. They converge on a single point, proving indisputably that these now separate landmasses were once a unified block, sharing a common magnetic history. This technique doesn't just prove they were connected, it allows us to create a precise timeline for their separation. By seeing when their polar wander paths begin to dramatically diverge, we can pinpoint the moment in geological history when the rift between them became an ocean too wide to share a magnetic story. Paleomagnetism transforms cold, hard rock into a dynamic historical document. Its pages written in the silent language of magnetic minerals, providing the most detailed and elegant proof of our planet's restless, mobile nature. The fragmentation of Pangea was not a single, clean break, but rather a grand, multi-stage divorce that unfolded over tens of millions of years. The initial crack that would become the North Atlantic was just the opening act. This colossal rupture effectively divided the supercontinent into two enormous, yet still massive, landmasses, Laurasia in the north and Gondwana in the south. Laurasia was a union of what we now know as North America, Europe, and much of Asia, while Gondwana was a sprawling assembly of South America, Africa, Antarctica, Australia, and India. For a time, these two new supercontinents faced each other across a narrow, young seaway known as the Tethys Ocean, but the tectonic forces were far from finished. The breakup of Pangea was not a single story. It was an anthology, and the separate tales of Laurasia and Gondwana's own fragmentation would write the next chapters of our planet's geographical evolution. The next great rift began to tear through the heart of Gondwana. While the North Atlantic was still widening, a new and equally powerful splitting event was initiated further south. Around 130 million years ago, the same process of mantle upwelling and crustal stretching that had split Laurasia now began to pull South America and Africa apart. This wasn't a simple continuation of the Northern Rift. It was a distinct event with its own unique character. The South Atlantic Ocean began to open, not like a zipper from north to south, but more like a door slowly swinging open from a hinge point in the far south near what is now the tip of Africa. This asymmetric opening meant that the southern continents separated at different times and rates, creating a much more complex set of geological borders. As the two landmasses drifted apart, the same volcanic processes filled the gap with new oceanic crust, creating the Walvis Ridge and Rio Grande Rise, a massive, submerged volcanic trail that traces the path of the South American plate over a mantle hotspot, a permanent scar on the seafloor marking this monumental separation. Simultaneously, on the other side of Gondwana, another dramatic departure was underway. The massive chunk of crust that is now the Indian subcontinent began to break free from the eastern side of Antarctica and the western coast of Australia. Propelled by immense forces from the mantle below, India embarked on what can only be described as a runaway northward sprint across the Tethys Ocean. This was one of the most rapid plate movements in Earth's history, with India traveling thousands of kilometers in a geologically brief period. In its wake, it left a brand new ocean basin, the Indian Ocean. The mechanism driving this was the formation of a new mid-ocean ridge system, a spreading center that pushed India northward and Antarctica southward. As India raced away, it left behind a trail of evidence, including the 90th Ridge, a near-perfect straight-line seamount chain on the Indian Ocean floor that acts like a fossilized track line of its incredible journey. The consequences of these separations were profound and immediate for the planet's climate and life. The opening of the South Atlantic and the Indian Ocean completely reorganized global ocean currents. The once enclosed seaways around Gondwana were now connected, allowing for the free circulation of water between the major ocean basins. This new circulation pattern would have dramatically affected heat distribution around the globe, likely contributing to climate changes that are recorded in the rock record from this period. Furthermore, the physical isolation of continents like South America, Australia, and India created spectacular natural experiments in evolution. Marsupial mammals, for instance, thrived in the isolation of South America and Australia, evolving into a dazzling array of forms that filled ecological niches taken by placental mammals on the still-connected northern continents. This secondary fragmentation didn't just create new coastlines, it created entirely new worlds of life. Meanwhile, to the north, Laurasia was undergoing its own, more gradual dissolution. The North Atlantic Rift continued to propagate northwards, slowly separating North America from Europe. This process was complex and piecemeal, involving the rotation of smaller continental blocks and the opening of several smaller seas, like the Labrador Sea, before the final connection was made to the Arctic Ocean. At the same time, the Tethys Ocean, which had once separated Laurasia and Gondwana, began to close as Africa moved northward and a series of smaller continental fragments collided with the southern margin of Eurasia, building mountain ranges and adding new pieces to the continental puzzle. The story of Pangea's breakup is therefore not one of simple fragmentation, but of a continuous, dynamic, and interconnected global reorganization. Each separation, from the grand parting of South America and Africa to the frantic dash of India, created its own unique set of fractures, ocean basins, and biological destinies, layering complexity upon complexity to create the beautifully intricate and diverse planet we call home today. While the grand story of continental drift often focuses on the massive movements of giants like Africa and South America, the breakup of Pangea was a far messier affair than a simple, clean split. The immense tectonic forces at play didn't just peel continents apart neatly. They shattered the edges, splintering off countless smaller fragments in a process that could be described as geological shrapnel. These orphaned pieces of crust are known as microcontinents and terrains, and their incredible journeys across the globe have added fascinating layers of complexity to the Earth's tectonic puzzle, creating a hidden world of miniature geological borders within our familiar continents. So, what exactly is the difference between these two? A microcontinent is, as the name suggests, a small continent. It is a piece of crust that is fundamentally continental in nature, composed of relatively light, buoyant granite rock, and is entirely surrounded by oceanic crust. The most famous example is Madagascar. This incredible island, a biodiversity hotspot teeming with unique life, was once snugly tucked into the coastline of what is now Somalia. As the supercontinent Gondwana began to break apart, a new rift system developed not between major landmasses, but right along the eastern edge of Africa. This rift successfully peeled Madagascar away from the mainland, sending it drifting eastward into the Indian Ocean, where it now sits as a solitary, massive fragment of ancient continent, a world unto itself. Another fascinating, though less known, example is the Jan Mayen microcontinent. Hidden beneath the frigid waters of the Greenland Sea, this submerged block of continental crust was sheared off from the edge of Greenland during the complex opening of the North Atlantic. It's a ghost of a continent, invisible from the surface but a very real piece of the planetary jigsaw. A terrain, on the other hand, is a more complex concept. It is a fragment of crust that has a geological history distinct from the continent it is currently attached to. Think of it not as a lone island, but as a foreign patch sewn onto a larger geological quilt. Terrains are often like tectonic hitchhikers. They travel vast distances on a moving oceanic plate before finally colliding with and accreting, or sticking onto the edge of a larger continent. The western half of North America is essentially a mosaic of these accreted terrains, a chaotic collage of crustal pieces that were scraped off the oceanic plate as it subducted beneath the continent. These terrains can be anything from ancient volcanic island arcs to small microcontinents themselves, each carrying its own unique rock record, fossil assemblage, and magnetic signature that is completely different from the rocks of the continent it slammed into. The significance of these wandering landmasses extends far beyond their intriguing origins, because they have often traveled long distances and evolved in isolation. They frequently host incredibly rare mineral deposits and unique ecosystems. Madagascar's status as a microcontinent is the direct reason for its astounding level of endemism. Over 90% of its wildlife is found nowhere else on Earth. Its long isolation allowed lemurs, tenrecs, and countless other species to evolve into forms unseen anywhere else. From a resource perspective, the journey of a terrain can concentrate valuable minerals. As it moves across the ocean, volcanic activity or the deposition of metals on the seafloor can create rich ore bodies. When that terrain finally crashes into a continent, it delivers a package of riches that might be completely alien to that region. The search for resources like gold, copper, or nickel often involves mapping these ancient, accreted terrains, as they are literal treasure chests delivered by plate tectonics. These fragments are more than just geological curiosities. They are vital pieces of evidence for reconstructing Earth's deep history. By studying the paleomagnetic data locked in the rocks of a terrain, scientists can trace its latitudinal journey across the globe, effectively mapping its ancient voyage. The fossil record within these rocks is equally telling. Finding tropical coral fossils in a terrain now located in a cold, temperate climate is a clear sign that this piece of crust has traveled a very long way. The process of accretion itself creates profound and lasting geological borders. The boundary where a terrain sutures itself to a continent is a zone of immense weakness, often the site of future earthquakes, mountain-building events, and volcanic activity. These ancient collision zones, hidden deep within the continents, continue to influence the landscape and the distribution of geological hazards millions of years after the collision occurred. The story of microcontinents and terrains is a powerful reminder that the breakup of Pangea was not a tidy divorce, but a chaotic and creative explosion that scattered pieces of the planet's history across the globe, each fragment carrying a unique story written in stone. For centuries, the greatest mystery in geology wasn't how continents moved, but whether they moved at all. The theory of continental drift, first proposed in a comprehensive way by Alfred Wegener in the early 1900s, was met with widespread skepticism. Scientists of the day asked a very simple yet devastating question. What possible mechanism could be powerful enough to move entire continents? Without an answer, the idea of drifting continents remained on the fringes of science, a fascinating but unproven hypothesis. The breakthrough, the key that finally unlocked the mystery, wouldn't come from studying the continents themselves, but from mapping the most unexplored region on Earth, the deep ocean floor. It was here that scientists discovered the irrefutable evidence for a process so fundamental, so powerful, that it acts as the very engine of plate tectonics, seafloor spreading. The story of this discovery is a masterpiece of scientific detective work, and it began with an unexpected clue from the Second World War. In the post-war years, governments began funding extensive mapping of the ocean floor, partly for submarine warfare purposes and partly for laying transatlantic telephone cables. Using new technology like sonar, scientists were astonished to discover that the seafloor was not a flat, featureless plain as everyone had assumed. Instead, they found a submerged landscape more dramatic than anything on land: vast mountain ranges, deep canyons, and towering volcanoes. The most stunning feature of all was the Mid-Atlantic Ridge, a continuous, massive underwater mountain chain that ran right down the center of the Atlantic Ocean, following the coastlines of the continents on either side with an almost perfect symmetry. This was the first major clue, but the real smoking gun was yet to be found, and it was hidden in the most unlikely of places: the magnetic memory of the seafloor's rocks. As research ships began towing magnetometers back and forth across the oceans in the 1950s and 60s, they weren't just mapping the depth of the water, they were measuring the magnetic properties of the rocks on the seafloor. What they found was utterly bewildering. The data didn't show a random, messy magnetic signal. Instead, it revealed a stunningly precise pattern: long, parallel stripes of alternating strong and weak magnetic intensity, all running perfectly parallel to the mid-ocean ridge. It looked like a gigantic, invisible barcode painted on the ocean floor. For the scientists studying these maps, like Fred Vine and Drummond Matthews, the pattern was instantly recognizable. They knew that Earth's magnetic field isn't stable. It has flipped its polarity hundreds of times throughout history, with the north and south magnetic poles swapping places. They also knew that when volcanic rock erupts at the mid-ocean ridge and cools, the iron-rich minerals within it lock in the orientation of the magnetic field at that exact moment. The stripes were a permanent record of these magnetic reversals, frozen in time. But the true genius was in the interpretation. Vine and Matthews realized that the pattern wasn't just a record of magnetic history, it was a record of creation. They proposed that as magma constantly wells up at the ridge, it forms new oceanic crust that is imprinted with the current magnetic field. Then, as even newer crust forms, it pushes that older crust outward, away from the ridge. The result is a symmetrical conveyor belt of rock, moving in opposite directions from the ridge, with matching stripes of normal and reversed polarity on either side. This was the undeniable proof of seafloor spreading. The entire Atlantic Ocean floor was acting like a twin-paged geological history book, with the mid-Atlantic ridge as the binding in the center, and each magnetic stripe representing a new chapter of formation. The implications were earth-shattering. It meant the ocean floor was not ancient and permanent, but young and constantly being renewed. This discovery immediately solved another long-standing puzzle: the age of the ocean floor. If scientists drilled down and pulled up cores of rock from the seabed, what would they find? The seafloor spreading hypothesis made a clear prediction. The rocks should get progressively older the farther you move away from the mid-ocean ridge. And that is exactly what the drilling programs found. The youngest rocks on the entire planet are always found right at the active spreading centers, sometimes literally still cooling from their recent eruption. As you journey away from the ridge toward the continents, the rocks get steadily older. The very oldest oceanic crust is found deep beneath the abyssal plains, and even then, it is never more than about 200 million years old, a mere blink in geological time when you consider that continental rocks can be billions of years old. This was the final, conclusive piece of evidence. The ocean floor is constantly being created at the ridges and eventually destroyed back into the mantle at deep ocean trenches in a great planetary cycle. This process is the powerful engine that Wegener was missing. The continents aren't plowing through the ocean crust. They are passive passengers on massive plates of lithosphere, being rafted along by the powerful, relentless conveyor belt of seafloor spreading, a process that continues to reshape our world every single day. And so, the very same tectonic forces that were redrawing the world map were also, quite literally, rewriting the book of life. The creation of these new, impassable geological borders, the widening Atlantic Ocean, the rising mountain ranges, the sprawling rift valleys, didn't just separate rock from rock. They separated population from population, setting the stage for one of the most powerful engines of evolution on our planet. This profound process is known as vicariance, a term that describes how a once continuous population can be split by the emergence of a new physical barrier. When a group of organisms is suddenly divided by something like a new ocean or a massive mountain chain, gene flow between them stops. They are now on independent evolutionary journeys, and over millions of years, those journeys will lead them to become entirely distinct species. The breakup of Pangea was the single greatest vicariance event in the history of complex life. a planetary-scale experiment in isolation and adaptation. Nowhere is this legacy more vividly on display than on the island continent of Australia. When it finally broke free from Antarctica around 45 million years ago, it wasn't just a continent drifting away. It was an entire ecosystem setting sail into biological solitude. The cargo it carried included a group of mammals known as marsupials, which give birth to tiny, underdeveloped young that complete their growth in a mother's pouch. At the time of the separation, marsupials were also present on other continents, but as Australia drifted into isolation, its evolutionary path diverged spectacularly. Shielded from competition with the placental mammals that came to dominate the rest of the world, animals like cats, dogs, and elephants that nurture their young fully inside the womb with an advanced placenta, the marsupials of Australia were free to experiment. In the absence of those competitors, they underwent an incredible evolutionary radiation, adapting to fill nearly every available ecological niche. The result is the breathtakingly unique fauna we know today. Kangaroos and wallabies evolved to become the grazers and browsers, occupying the roles of deer and antelope. The koala became a specialized tree leaf eater. The Tasmanian devil became a formidable scavenger and predator. Even a mole-like lifestyle was achieved, not by a placental mole, but by the marsupial mole. This entire parallel universe of mammals is a direct, living consequence of a geological event that occurred tens of millions of years ago. A similar, though equally astounding, story unfolded on the microcontinent of Madagascar. When it rifled away from eastern Africa, it carried with it a small population of primitive primates. Isolated on this vast island, these early ancestors embarked on their own unique evolutionary trajectory. Over 50 million years of isolation, they diversified into the incredible array of creatures we know as lemurs. Every single species of lemur, from the tiny mouse lemur to the iconic ring-tailed lemur, is found nowhere else on Earth. They evolved to fill niches that on the African mainland were taken by monkeys, squirrels, and even woodpeckers. The eye, with its bizarre elongated finger for extracting insects from wood, is a perfect example of this unique evolutionary creativity born from long-term isolation. Madagascar became a natural laboratory, and the experiment's controlling variable was its geological separation from a larger landmass. This phenomenon of vicariance isn't just about mammals on far-flung continents. It's a universal principle written into the DNA of life everywhere. We see it in the freshwater fish species found in rivers on opposite sides of the South Atlantic, whose ancestors once swam in the connected waterways of West Africa and eastern South America. We see it in the ancient plant families whose fossils are found scattered across all the southern continents, their modern descendants now separated by thousands of miles of ocean. The initial geological division creates the isolation, and from that isolation springs forth novelty, diversity, and the breathtaking variety of life that covers our planet. It's a powerful reminder that the history of biology is inextricably linked to the history of geology. The ground doesn't just provide a stage for life, its movements directly orchestrate the evolutionary symphony. The very borders that divide continents and oceans are, paradoxically, the same forces that create the rich tapestry of biodiversity, proving that in the grand story of our planet, separation is not an end, but a brilliant and creative new beginning. For centuries, the story of Pangea's breakup was a narrative written in fragments, pieced together by painstaking surface observations and a great deal of deduction. Geologists were like detectives trying to solve a colossal crime with only a handful of clues left at the scene. They could see the matching coastlines and similar mountain ranges, but the deep, hidden structures, the failed rifts, the buried sutures, the mantle plumes remained shrouded in mystery, subjects of intense speculation. Today, that has all changed. We are no longer limited to surface clues. We have developed a suite of technological superpowers that allow us to peer directly into the Earth's interior, to map its hidden anatomy with stunning precision, and to turn the ancient story of continental drift from a compelling theory into a detailed, observable fact. One of the most revolutionary tools in this new arsenal doesn't even require touching the ground. Satellites orbiting high above the planet can measure the Earth's gravitational field with exquisite sensitivity. Because gravity is slightly stronger over areas of denser rock and slightly weaker over areas of less dense material, these satellite-based gravity measurements allow scientists to create detailed maps of mass distribution beneath the surface. This technology, known as gravimetry, can reveal the ghostly outlines of ancient geological structures invisible to the naked eye. A failed rift arm, a buried mountain root, or a dense slab of subducted oceanic crust. All of these features create subtle gravitational anomalies that a satellite can detect from space. It's like having an X-ray vision that can scan entire continents, revealing the hidden scars and sutures from Pangea's assembly and dissolution as clear as day on a map. But to truly understand the three-dimensional architecture of these subterranean borders, we need to go beyond gravity and listen to the Earth itself. This is the domain of seismic imaging, a technology that has undergone a quantum leap in recent decades. Instead of relying on occasional natural earthquakes, large-scale projects like the U.S. Array component of the EarthScope initiative deployed thousands of seismic sensors across North America in a dense, moving grid. This massive network acted like a colossal CT scanner for the continent, using the seismic waves from distant quakes as its energy source. As these waves travel through the Earth, they speed up or slow down depending on the temperature and density of the rock they pass through. By analyzing the vast amounts of data from these sensors, supercomputers can construct breathtakingly detailed 3D models of the subsurface. This is how we discovered the precise geometry of the ancient Farallon plate slab still sinking deep beneath the continent, or mapped the complex fingers of the Yellowstone mantle plume reaching hundreds of kilometers into the mantle. These images provide irrefutable visual evidence of the dynamic processes that have shaped our continent, directly linking present-day geology to the forces that broke Pangea apart. Of course, some of the most crucial evidence for continental drift lies at the bottom of the ocean, and getting there requires a different kind of technological marvel. Deep-sea submersibles and remotely operated vehicles, or ROV, are now capable of descending to the most extreme depths, allowing us to explore the very factories where new crust is born. These robotic ambassadors can navigate the treacherous terrain of the mid-Atlantic ridge, collecting pristine rock samples from volcanic vents, filming unique ecosystems that thrive on chemical energy, and directly observing the processes of seafloor spreading in real time. They are our eyes and hands in a world of perpetual darkness, providing ground truth evidence that complements the broad view from space and the deep vision from seismology. Perhaps the most patient and persistent of these scientific endeavors are the international ocean drilling programs, projects like the long-running JOIDS Resolution and its successor, the Vessel Chikyu. These are essentially floating laboratories capable of drilling miles down into the oceanic crust and even into the upper mantle. By extracting long, continuous cores of sediment and rock from the seafloor, scientists can read the history of the ocean basins like the rings of a tree. Each core sample provides a direct record of climate change, magnetic reversals, and biological evolution. Drilling into the sediments on the eastern margin of North America, for instance, allows us to study the exact sequence of events during the initial rifting phase, pinpointing when the land first cracked and when the ocean first flooded in. This isn't indirect evidence, this is holding a piece of the story in your hands, a tangible record of Pangea's divorce papers. The convergence of all these technologies, from orbital eyes to deep-sea drills, has created a golden age of geological discovery. We are no longer just inferring the past, we are observing it directly in the present. We can trace the path of a mantle plume from its origin at the core mantle boundary to its expression in a volcanic chain on the surface. We can map a suture zone under a city and understand its potential to generate earthquakes. We can see the failed rifts that never became oceans, frozen in time beneath the Midwest. This unprecedented view is transforming geology from a historical science into a predictive one. By understanding the precise mechanics of how Pangaea broke up, we gain a powerful lens into the future, allowing us to model how our continents will continue to evolve, where new resources might be found, and how to better prepare for the geological hazards that arise from our planet's restless, dynamic nature. The veil has been lifted, and the Earth's deepest secrets are finally being revealed. And just as the breakup of Pangaea set the stage for our world today, the relentless engine of plate tectonics ensures that the story is far from over. The geological borders we've been exploring, those hidden scars and sutures, are not permanent fixtures on a static planet. They are merely the current configuration in a slow-motion dance that has been ongoing for billions of years and will continue for billions more. So what does the future hold? If we could hit fast forward and watch the next 250 million years unfold, we would witness a planet that is almost unrecognizable, with new oceans, new mountain ranges, and an entirely new supercontinent forming from the ashes of the old. One of the most dramatic predictions involves the eventual closure of the very ocean that Pangaea's breakup created, the Atlantic. While it is currently still widening, the forces that drive it will not last forever. The subduction zones that currently consume old oceanic crust are primarily located around the Pacific Ocean, in the famous Ring of Fire. But there is evidence that new subduction zones are already trying to form at the edges of the Atlantic. For instance, off the coast of Portugal, a region known as the Gibraltar Arc may represent the earliest stages of a new subduction zone. If this process takes hold, it could spell the beginning of the end for the Atlantic Ocean. The dense, old oceanic crust of the Atlantic floor could start to be pulled back down into the mantle, gradually dragging the Americas back towards Europe and Africa. This wouldn't be a gentle reunion. It would be a colossal, slow-motion collision that would weld the continents back together, likely pushing up a new mountain range that would dwarf the Himalayas, a modern-day Pangaean-scale event that would utterly redefine the world map. This very process leads to the most compelling forecast from geologists, the formation of the next supercontinent, often referred to as a major. There are several models for how this might happen. The introversion model suggests the Atlantic will close, bringing the Americas back to collide with Eurasia and Africa. The extroversion model proposes the Americas will continue to drift west, sweeping around the Pacific until they collide with Asia, fusing together along the current Pacific Rim. And a third model, orthoversion, suggests the continents will all converge and assemble around the North Pole. While the exact configuration is debated, the underlying principle is not. The continents are on a cyclical journey of assembly and dispersal. The same forces of mantle convection that tore Pangaea apart will eventually bring its fragments back together again, creating a new supercontinent that will host its own unique climates, ecosystems, and perhaps future intelligent life that will ponder the geological borders we left behind. But we don't have to look hundreds of millions of years into the future to see this process in action. It's happening right now in Africa. The East African Rift System is the most significant example of active continental breakup on the planet today. This massive network of valleys and volcanoes is slowly but surely tearing the African plate in two. The eastern portion, the Somali plate, is pulling away from the rest of Africa, the Nubian plate. In perhaps 10 to 50 million years, the rift will have sunk low enough for the Indian Ocean to come flooding in, creating a new seaway that will eventually widen into a full-fledged ocean. This will leave the Horn of Africa and much of East Africa as a massive island, drifting off into the Indian Ocean, much like Madagascar did long ago. This isn't speculative fiction. It's a process we can measure with GPS, watch through volcanic activity, and feel through the frequent earthquakes that shake the region. It is a living, breathing demonstration of how supercontinents are born from the fragmentation of their predecessors. While these processes operate on timescales that are almost incomprehensible to human civilization, their long-term implications are profound. Understanding the trajectory of plate tectonics allows us to make better decisions about resource management. The formation of new mountain ranges and rift valleys will create new mineral deposits and hydrocarbon traps. Knowing where these geological events are likely to occur could guide far future exploration. More immediately, it helps us with hazard mitigation. The zones where continents are actively colliding or rifting are the same zones that will experience the most intense earthquakes and volcanic activity for millions of years to come. By identifying these areas of future tectonic strain, we can better prepare the infrastructure and societies of the distant future for the inevitable geological upheavals they will face. The Earth's story is one of constant dynamic change. The borders we see today are temporary, and the forces that forge them are already at work, quietly and inexorably drawing the map of the world to come. Now, while the hard evidence of rocks and fossils gives us a scientific timeline, there's another, more human layer to this story, one written not in stone but in myth and memory. For thousands of years, long before the concepts of plate tectonics or supercontinents existed, cultures around the world have been telling stories that seem to echo the colossal geological events of the deep past. These narratives aren't literal records, of course, but they represent a profound and intuitive human attempt to explain a dynamic world. A world where lands could flood, mountains could rise, and continents could feel strangely connected. They are the cultural and mythological fingerprints of Pangea's breakup, a haunting echo of planetary change preserved in the oral traditions of our ancestors. Consider the sheer universality of the Great Flood myth. From the Epic of Gilgamesh in Mesopotamia to the story of Noah in the Hebrew Bible, and from the ancient Greek tale of Deucalion to the Manu legend in Hindu texts, cultures on every continent have a story about a world-engulfing deluge. For a long time, scholars debated a common source, but what if the commonality isn't a single flood event, but a shared, deep-time memory of something even more dramatic? The very process of continental separation involved immense, gradual flooding. As the continents drifted apart, the land between them subsided, and the ocean rushed in to fill these colossal new basins. For the creatures living at the time, this would have been a cataclysm of unimaginable scale, a slow-motion inundation that drowned entire worlds over generations. It's not difficult to imagine how the fading memory of such an event, passed down for thousands of years, could eventually become mythologized into a story of a divine flood sent to punish humanity. These stories could be a distant, cultural reverberation of the actual rising seas that accompanied the birth of our modern oceans. We can find similarly powerful metaphors in the creation stories of indigenous cultures with deep ties to their land. The Aboriginal Dreamtime stories of Australia, which represent one of the oldest continuous cultural histories on Earth, are rich with themes of land formation and separation. Many of these stories describe a time when the world was flat and featureless, until ancestral beings moved across the landscape, shaping mountains, carving riverbeds, and creating the sacred sites that define the continent. Crucially, some of these narratives also speak of a time when lands now separated by water were once connected. While these are spiritual accounts of creation, they demonstrate a sophisticated understanding of the landscape's dynamism, a sense that the world was not always as it appears today. This intuitive grasp of a changing Earth resonates powerfully with the scientific narrative of Australia's separation from Antarctica, a physical divorce that isolated its unique life and culture. Looking north, the Norse myths of Midgard also offer a fascinating parallel. In their cosmology, Midgard, the world of humans, was often depicted as a landmass surrounded by a vast, impassable ocean. This ocean was not empty. It was home to the monstrous Jormungandr, the Midgard serpent, a creature so immense it could encircle the entire world and bite its own tail. This mythic geography can be read as a powerful metaphor for the terrifying and unknown power of the sea. For a seafaring culture like the Norse, the ocean was both a highway and a horrifying abyss, a force that could separate families and homelands with its immense, unpredictable power. The serpent encircling the land is a perfect symbolic representation of the ocean's isolating embrace. Much like the newly formed Atlantic Ocean severed the connections between continents, creating a watery barrier that would define human exploration for millennia to come. These stories are far more than just curious coincidences. They represent a fundamental human desire to find meaning in the landscape. Geology provides the stage, and culture writes the plays performed upon it. The distribution of languages, the paths of ancient trade routes, and the very location of our greatest cities are all, in some way, dictated by the geological borders we've explored. A mountain range determines a cultural boundary, a river valley becomes a cradle of civilization, a rich mineral deposit becomes the heart of an empire. Our myths are often the way we process these grand, environmental forces that shape our lives. They are a testament to the fact that humans have always been keen observers of nature, and even without our modern tools, they sensed the incredible power and history written into the very ground beneath their feet. These cultural narratives are a bridge connecting the cold, hard facts of geological science to the warm, beating heart of human experience, reminding us that our story is forever intertwined with the epic story of the Earth itself. Understanding the immense forces that shaped our planet is far more than an academic exercise. It's a fundamental key to navigating the world we live in today. This knowledge of Pangea's breakup and the hidden borders it left behind transforms our perspective from mere inhabitants of the Earth to informed participants in its ongoing story. It fosters a profound sense of deep time, allowing us to see the ground beneath our feet not as a permanent stage, but as a dynamic page in a multi-billion-year history book. This awareness cultivates a deeper appreciation for our place within this grand narrative, humbling us with the scale of geological time while simultaneously empowering us with the knowledge to make smarter decisions for our future. It connects us to a past where the very continents were on the move, reminding us that change is the only constant on our planet. This geological literacy has immense practical value, directly informing critical fields that shape our modern society. In environmental science, we can't hope to address climate change without understanding the long-term processes that have governed Earth's climate for eons. The opening of the Drake Passage and the subsequent Antarctic circumpolar current, for instance, show us how the rearrangement of continents can trigger global cooling and the formation of ice sheets. This deep time context is essential for distinguishing natural climate cycles from human-induced change. For engineers and urban planners, this knowledge is vital for assessing seismic risk. Building a city, a dam, or a nuclear power plant requires understanding the ancient fault lines and sutures hidden below, as these zones of weakness are where future earthquakes are most likely to occur. Recognizing that Charleston, South Carolina, sits atop a reactivated rift fault completely changes the calculus for constructing resilient infrastructure in that region. The relevance extends directly to resource management and our everyday lives. The device you're watching this on right now contains minerals like cobalt and copper, whose distribution was largely determined by the rifting of continents. The gasoline in our cars and the natural gas heating our homes often come from oil-rich basins that formed as North America and Africa pulled apart. Understanding these ancient geological connections allows us to explore for these resources more efficiently and with a smaller environmental footprint, reducing the need for disruptive and widespread exploratory drilling. It helps us locate vital groundwater aquifers that are often stored in the porous rocks of ancient rift valleys. From the materials in our technology to the energy that powers our society, the legacy of Pangea is woven into the very fabric of our daily existence. For educators, this topic is a golden opportunity to ignite a passion for science. The story of continental drift has all the elements of a great mystery: puzzling clues, intrepid detectives, and a revolutionary conclusion that changed everything. Teachers can bring this to life in so many engaging ways. Students can use simple puzzle pieces to reassemble the continents, experiencing the same aha moment that Alfred Wegener did. Interactive digital simulations allow them to fast forward through millions of years of tectonic movement, watching oceans open and close with the click of a button. For those lucky enough to live near key geological sites, a field trip to a local road cut can reveal layers of rock that tell a story of ancient deserts, shallow seas, or volcanic eruptions, all part of the larger saga. Even a simple world map becomes a tool for discovery, inviting students to trace the matching coastlines and speculate about the fossil evidence that proves the connection. Ultimately, this isn't just about memorizing the names of ancient supercontinents or the mechanics of plate tectonics. It's about developing a way of thinking, a geological mindset that emphasizes connectivity, deep time, and evidence-based reasoning. It teaches us to look beyond the surface and question how the world came to be the way it is. This mindset is crucial as we face global challenges like climate change, resource scarcity, and natural disasters. By learning from the Earth's past, we gain the wisdom to build a more sustainable and resilient future. The story of Pangea's breakup shows us that our planet is a complex, interconnected system, and that to understand our present and future, we must first learn to read the deep history written in the stone beneath our feet. Reconstructing the precise story of Pangea's breakup is like trying to solve the world's most complex jigsaw puzzle, only to discover that most of the pieces are missing, others are damaged, and the picture on the box is incredibly faded. The first and most obvious challenge is one of sheer inaccessibility. The very evidence we need to understand continental drift is often locked away on the deep ocean floor under miles of dark, crushing water. We have better maps of the surface of Mars than we do of our own seafloor. Sending submersibles or drilling ships to these abyssal plains is a monumental technical and financial endeavor, limiting our ability to directly sample the oceanic crust that holds so many answers. Every core sample pulled from the seabed is a precious data point, hard-won from an environment as hostile as outer space. Even when we have the rocks, interpreting their story is fraught with difficulty. The continental rock record is not a neat, continuous timeline. It's a fragmented archive full of missing chapters. Imagine a history book where entire eras have been ripped out, the remaining pages scrambled, and then the whole thing has been baked, twisted, and eroded for millions of years. That's what geologists work with. Mountain-building events bury and metamorphose older rocks, obscuring their original features. Erosion strips away entire layers of history, leaving behind gaps called unconformities, silent, billion-year gaps in the story where we can only guess what happened. Piecing together the sequence of events from this mangled record requires brilliant detective work and a heavy reliance on correlating tiny, scattered clues across vast distances. This is where the power of interdisciplinary collaboration becomes absolutely essential. No single scientist or field can solve this puzzle alone. It requires a full-scale intellectual alliance. Geophysicists use seismic waves to create CT scans of the Earth's interior, revealing the ghostly outlines of ancient slabs subducting into the mantle. Chemists analyze the precise isotopic signatures of rocks, which act like unique fingerprints that can trace a rock's origin and age. Physicists model the complex fluid dynamics of the mantle's convection currents in powerful supercomputers. And paleobiologists provide the crucial biological testimony, using the distribution of fossils to confirm the former connections between continents that the physical data suggests. It's only at the intersection of all these fields that a coherent picture begins to emerge. Despite this incredible collaborative effort, significant debates still rage, proving that science is a living, breathing process of debate and discovery. One of the biggest ongoing discussions centers on the exact role of mantle plumes. Are these colossal upwellings of hot rock from the deep mantle the primary instigators of continental breakup, literally burning a hole through a supercontinent from below? Or are they merely passive bystanders, rising up to exploit weaknesses that were already created by the stretching and pulling of plate tectonics? The evidence is still hotly contested. Similarly, pinning down the exact timing of key rifting events is a constant challenge. Refining the dates by even a few million years can completely change our understanding of the cause and effect relationships between volcanic activity, extinction events, and the opening of new seaways. Each new discovery, whether it's a freshly dated rock layer from a remote outcrop or a new gravity anomaly map from a satellite, has the potential to overturn a long-held belief and send scientists back to the drawing board. This isn't a sign of failure, it's the very engine of scientific progress. Every answered question inevitably leads to 10 new, more nuanced ones, driving us closer to an ever more detailed understanding of our planet's magnificent and dynamic history. The best part about this incredible story is that you don't need a PhD or a supercomputer to start exploring it for yourself. This science is literally all around us, waiting to be discovered with just a little bit of curiosity. Let's talk about some hands-on ways you can become a detective of deep time right from your own home. One of the most immediate and powerful things you can do is to simply pull up a world map on your screen, but this time look at it with a geologist's eyes. Forget the political borders and country names for a moment. Instead, focus purely on the shapes. Look at the incredible, almost puzzle piece fit between the bulge of Brazil and the coastline of West Africa. Now try to mentally close the Atlantic Ocean. Can you see how they once locked together? Zoom in on the North Atlantic and trace the coast of Norway. See how it seems to slot perfectly against the eastern edge of Greenland. This simple act of observation, of seeing the continents not as fixed entities but as mobile pieces of a grand planetary puzzle, is the first step toward a completely new way of seeing our world. To take this a step further, there are some fantastic free online tools that bring this concept to life in a dynamic way. The PaleoMap project and various interactive globes available on geology websites allow you to slide a timer bar through hundreds of millions of years. You can watch the slow-motion dance of the continents unfold right before your eyes, seeing exactly where your hometown was located during the age of the dinosaurs or when it was buried under a shallow sea. It's a profoundly humbling and exciting experience to type in your city and see that it once sat on the coast of an ancient, long-vanished ocean or was nestled deep within the heart of a supercontinent. These tools transform abstract concepts into a personal journey through time, connecting your place in the world today to the epic saga of Earth's history. Perhaps the most satisfyingly tactile experiment is the simplest. Get yourself a pair of scissors, some cardstock, and a printed map of the world. Carefully cut out the continents, and then, like a scientist from a century ago, try to reassemble them into Pangea. You'll quickly discover that it's not just about the coastlines. You have to consider the continental shelves, the submerged edges of the continents that extend far out under the ocean. When you include these, the fit becomes even more astonishing. This isn't just a craft project. It's the same exercise that early proponents of continental drift used to convince a skeptical scientific community. You're replicating a key part of the scientific process, and in doing so, you'll gain an intuitive understanding of the evidence that first hinted at our mobile planet. And you don't have to travel to a Grand Canyon to find evidence of this ancient world. It might be right in your own community. The next time you're out for a walk, take a closer look at the local rocks. In a creek bed, a road cut, or even a building made of stone, you might find clues. That reddish sandstone could be the petrified dune of a vast desert that once existed in Pangea's interior. Those layers of shale might be the compressed mud from an ancient lake bed. If you're near a mountain range, even a small one, you might be looking at the worn-down roots of mountains that were once as tall as the Himalayas. Many state geological surveys publish free guides to local rock formations, turning an ordinary hike into a thrilling treasure hunt for pieces of our planet's deep past. Every rock has a story to tell, and you just need to learn how to listen. So as we pull back from this incredible journey, from the unified supercontinent of Pangea to the beautifully fragmented world map we know today, it becomes overwhelmingly clear that these ancient events are not locked away in some distant past. They are actively scripting our present and will continue to shape our future in ways both profound and personal. Those hidden geological borders, the deep sutures, the submerged fracture zones, the bisected mountain roots are far more than just lines on a geologist's map. They are the invisible architects of our reality, dictating where we find the energy to power our cities, the minerals to build our technology, and the fertile grounds to grow our food. They guide the paths of ocean currents that regulate our climate and mark the zones where the Earth occasionally shudders to remind us of its restless power. This deep history is the ultimate context for every modern challenge we face, from managing scarce resources in a growing world to preparing our communities for natural hazards in a changing climate. Understanding that the ground beneath us is dynamic, not static, is the first step toward building a more resilient and sustainable future, because we are not separate from this planet. We are living upon its ever-changing canvas. The great Canadian geologist J. Tuzo Wilson once offered a perfect summary of this grand reality when he said, "The Earth is a machine that operates on its own timetable." This isn't a machine of gears and levers, but a magnificent, complex system of heat and rock, of unimaginable forces and patient million-year rhythms. Our human timeline, with all its urgency and hustle, is but a fleeting moment in the planetary deep time that governs this machine. Recognizing this doesn't diminish our importance. It connects us to something truly epic. It fosters a profound humility and a powerful sense of stewardship, knowing that we are the temporary custodians of a world that is still very much in motion. The story of Pangea is, in the end, our story too, a narrative written in stone, encoded in our landscapes, and echoed in the very DNA of the life it isolated and diversified. It's a reminder that to understand who we are and where we are going, we must first learn to read the magnificent history buried beneath our feet. I'd love to hear which of these hidden geological borders fascinates you the most. Was it the bisected Appalachian Caledonian mountain chain, the volcanic trails of the New England seamounts, or the earthquake zones along ancient Sutures? Share your thoughts in the comments below, and if you enjoyed this deep dive into Earth's mysteries, be sure to subscribe and hit the bell so you don't miss our next journey into the wonders of our planet.